believe we are live. Let's find out. We are. Okay. Let's see. Twitch is not updating, or not Twitch, OBS. That's why we check these things.
I apologize for interrupting.
Yes.
Did you by chance leave a Microsoft Surface power supply in here after your class?
I did not.
Last week? Okay, cool. We found one in like whatever tomorrow morning would be. So.
I appreciate it.
Yep, take care.
All right. Sorry for the delay there, Twitch. Give me 1 second. I want to make sure you see what I see. What do I want? Transform, fit to screen, mash down here. Do we see it, Twitch? I think we do. All right. The last and final challenge. Do the slides work? Yes, we have the technology. Okay, so today is February 13th, I believe. We are on week 6 of CSE, what is this, 598? Yes. Our topic is dynamic allocator misuse. So, I'm going to start with memes. We had some good memes this week, guys, all right? Not only in my opinion, but I believe other people even commented on the quality of our memes, all right? We are showing 365 how to make good memes. 365 is starting to produce good memes. This is good, all right? And if anyone from 365 happens to be catching this stream, post some good memes. I'll include them on my slides, all right? I don't care if they're topically not relevant. Good memes get acknowledged. Okay, so first thing, as I kind of mentioned last week, the vtable is kind of the monster of the file struct module. And I think everyone kind of agreed that that was the case, right? I know there were people that got there early and did manage to get through it, and it was the dominant topic of office hours last week, right? Hopefully you found that helpful, right? We're going to be doing more stuff with pointers and structs right now. So hopefully we have our kind of head wrapped around that. One thing that I think is not vtable related, but is totally relevant, is my insane way of phrasing things, right? When I say read, I'm talking about the read syscall. Read writes to memory. Writing to memory is an arbitrary write. And we're going to see the same kind of backwards, counterintuitive logic in how I named things in my demo code that I wrote before class here. I am referring to the syscall, not necessarily the primitive. Other memes. GDB, always, always a winner. If this was your approach for baby file, of just starting the challenge, stepping through it in GDB, and kind of reasoning about the assembly, and then changing something, trying it again until you got the flag, it's great, okay? Even if you had to do it every single time from the beginning fresh, for every challenge, you are learning valuable skills here. Because it's not about, can I memorize how file structs work? It's about, can I reason about what is going on with these pointers and how I think about structs and what's going on in memory? And so I would argue that doing this is probably the more valuable practice than being like, oh, I have memorized the layout of a file struct. And then this one, I should have looked it up. I wanted to look up what pumpkin Q is, right? I still don't know. I didn't have time. But this was just an awesome meme that emerged from office hours. So whoever posted that, I thought it was hilarious, and so did Jan.
Unpacks and interleaves the low order data elements of something?
It unpacks and interleaves the
low order data elements.
The low order data elements of something.
Yes.
Right? That's what happens when you have a complex instruction set, right? For something much simpler, try the ARM dojo. All right. This is a 365 meme, and I think it's worth mentioning because you know what 365 is doing as of right now? Reverse engineering.
Oh boy.
So, any of you who have taken 466, you should know that the dojo tends to just absolutely burn down when 365 is dealing with reverse engineering. In particular, IDA, right? I don't know when their due date is. I'm sure we could look it up and see, but just be aware of that. As 365 goes through bursts of people discovering the tab button in IDA, IDA will not work. And so keep that in mind as you plan as far as how you're going to allocate your time on this module. All right, course schedule here. We are plugging along at a decent clip. We are on kind of the first module of HEAP. The next 3 weeks are going to be focused on HEAP. This module specifically is just about the T-cache. I know in the lecture video someone mentioned to me that Jan refers to large bin, small bin, kind of more complicated HEAP stuff. The only thing that we need to do in this module is T-cache. The entire module. All right. Then we'll go into primitives and memory mastery. This is kind of like a midterm as far as difficulty. So if you remember, what was it, toddler sis and toddler, it's some other toddler, right? It's going to be a similar difficulty to that. So when people say, I hate race conditions will exist in this module. It is not what I'm trying to teach you, but it is necessary from level 1. All right? So just know that as far as planning your time. I don't intend on modifying the challenges here, so if you do have time to work ahead or want to take a sneak peek at it, feel free to look at the public stuff. I don't think I'm going to change it before it gets released. And then right before spring break, we're going to do advanced HEAP. This is where we're going to look at fast bin, large bin, small bin, all these other crazy things that aren't T-cache, right? And there are dedicated lecture videos that are in this third module here that go into detail as far as how these other bins work. So this week, what we care about is T-cache and only T-cache. Grades. So, how did we do? What did we just do? File struct exploits? Well, that looks pretty good, guys. All right, I gotta say, as far as quartiles go, we're pretty solid here, right? I want to say almost everyone got 100% on this module. There were a couple outliers here, but as a whole, we crushed it. I'm glad to see it. Good job to everyone. Why does that say memes? Because I can't make a slide. Copy paste let me down. So this is where we're at. Orange is today's average, and we see that for file structs, it's very similar to format strings, where the average was somewhere around like 87 or so. So again, everyone is doing quite fine there as far as the class is concerned. What do we got here? This is solve rate. I've noticed something. I did spend a little bit of time looking at this one. People are starting to solve things earlier. It's impressive to me, right? Here was speculative execution, because remember, this is all dated to this is t=0 when the module is released. And we see that now, if we look at like format strings, people are starting, this is probably about Sunday, right? Saturday, Sunday is when we start seeing our first new solves. And we see that being the case here as well with the HEAP module, which is awesome, right? That means as far as this kind of shared module time with these 10-day overlaps, you guys, for the most part, are on the early end of the curve, right? Which is good. I'm glad to see it. Overall, this is through the file structs module. The class average is a 77. Now, that isn't in my opinion, accurate number, because there are a number of students that simply haven't solved anything from the past couple modules. I don't know if they just haven't decided to drop, but they're on the roster. I also haven't updated the roster, so they may have decided to pursue another course, which is totally fine. If we talk about the students who are tackling the material, as in you have at least one solve in modules, the class average is a 91.44. This is including extra credit, all right? Somebody asked for extra credit to be posted on the 12th. I just cannot make this follow me.
Put a ping pong ball on your head. You like those, right?
I don't know what it is, man. I'm just too animated. Okay. So the class average is an A, as far as people who are actually solving challenges here. So I feel like everyone's doing well. If you have any questions about the grade, please reach out to me on the Discord or in person. I'm more than happy to discuss that. You can view your grade. I mentioned this on topic, but it's worth reiterating here. One of the kind of challenges with the grading page is we always have an assignment that's due, which means that it is always showing that you have, a 0 or whatever your status is on the current module. If you want to look at stuff that is already finished, you can go to the grade page and then append (ignore pending) to the grades page, and that will calculate your grade without whatever is actively assigned. So that should give you a much better idea. It does make a big difference. So if you have been looking at your grade page just like, oh, this is horrible, do this. Hopefully you'll feel a little bit better. Module tips for this module. Level 16 plus, pain. Okay? There's no getting around it. Every student hates levels 16 through 20. The reason everyone hates levels 16 through 20 is because 16 through 20 utilize something that's called safe linking. When this module was originally released, it used what was the current libc at the time. However, in the year since its initial release, libc is updated. There are new mitigations that exist in the heap. It isn't fair, or in my opinion, fair or right, to teach you heap and not teach you about what is the current implementation of the heap. So levels 1 through 15, use the old stuff. Use the old libc. This is good because it allows you to focus on the things that we're trying to discuss, right? Understand how the metadata works, what the layout is. It's a lot less messy. 16 through 20 has this whole safe linking XOR insanity thing going on that students hate. It is very important that you get to 16 through 20 here, because next week, I said, is kind of like a midterm as far as difficulty. It relies on heap. Every single one of those challenges has safe linking enabled. What this means, this is your opportunity to learn how safe linking works, because next week there'll be safe linking on every single challenge. 2 weeks from now, when we do deeper into the heap, some of the bins utilize safe linking. You will experience safe linking again. And if there are any additional challenges that rely on heap for the remainder of the semester, it will have safe linking. So this is one of the few modules when I highly, highly encourage getting to the end, because otherwise you will be at a significant disadvantage. Demo plans is apparently nothing. Pretty cool. Does anyone have any questions for me before I do the demo that is not shown on this slide? No? Cool. So, what I wrote is a super generic heap challenge. Helps if I can type. Cool. So in general, when you're talking about heap challenges or CTF challenges, if you see something that looks like this, where you have a menu and you can create some type of object and then destroy some type of object, this could be like a notes application, is a common representation, odds are it is a heap challenge, right? Because this is kind of the most straightforward way of allowing you to interact with the heap and not obscure it, okay? So this is very similar in kind of setup to the challenges in this module, where we have the ability to malloc something, free something, read. This is going to call read, which means we are writing to memory, write, and then print val. In this case, val is just some global here, not so secret value. We're going to read a number, 1 through 5. Based upon that number, we're going to prompt for a size and a slot. Based upon the size and slot, we will malloc free, read, write, as this makes sense. Does anyone have any question about the C code that we're looking at here? There's probably a typo. We'll see. And then the very last option will printf the global. All right, and this is just so that we can kind of reason about what's going on here. So here it is. Now, what tool do you think I'm going to recommend we use to reason about the heap? GDB, yes. Now, these challenges, the 0.0 challenges, do a great job of printing out the T-cache. Right? I really like how they work and how they display information, and so that is great for understanding and kind of reasoning about what's going on. But in reality, like, you're not going to get that every time, right? So instead, GDB, we'll use GDB, because GDB can do this for us. I'm using Jeff. All right, so let's malloc something. It's going to ask for a size. It's going to ask for a slot. This slot can be anywhere from 0 to 15. I have 16 slots. It's, like I said, very similar to the challenges that you've seen. So I said I want to malloc something of size 28 into slot 0. What is the state of the T-cache right now? You be quiet, sir. Yeah, you've already completed the module, right? Yeah. Okay. All right. How about if I malloc something of size 28 again, and we put it in slot 1? What's the state of the T-cache? Still nothing. Why?
Because we haven't freed anything yet, so there's nothing like hanging around.
Right. The comment was we haven't freed anything yet. The T-cache is where already, or allocations that have already been kind of provided, when they are freed, are cached, hence the term T-cache. This is a thread local cache where we are storing allocations that when they are freed, in case they need to quickly be reused, right? This is a performance optimization.
Good question.
Yes.
If we were to like spin off a child process off of this, that would have its own T-cache, or?
So the question is, if we were to spin off a child process of this, would it have its own T-cache? If I spin off a thread, it does, because it's a thread local cache. Now, if I just fork, all right, I'll defer to you here. If I just fork, isn't it the same, because it's going to clone virtual memory, wouldn't it be the same heap?
They have its own virtual memory, so they are different virtual
But the prior heap state should be copied, right?
Yes.
Because it's copy on write. So it would be its own heap, right? But the state of the heap of the child process would be consistent with the parent at the time of fork.
Okay.
Do you agree? Okay.
But then any future changes would be applied to like two separate.
Correct.
Okay.
So in general, when you call fork, if nothing has explicitly been like mapped or shared, or we're just kind of have a normal running process. When you call fork, all virtual memory is copied into the child process. Now, this is actually copy on write as a performance optimization. So the state of the heap mapped memory will be consistent in the child with the parent. But any actions that go forward that mutate the heap would not be reflected in the parent. Good question. Okay, so we said I have to free something. So if I say I want to free 1, what do we think is the state of the T-cache? You're making faces over there, but what's going on in the old noggin?
I think it should have 1 entry now.
Okay, the T-cache should have 1 entry. So I'm going to hit Control-C so that we're in GDB. There are heap commands inside. These are not GDB specific, this is Jeff specific. All right, so we have heap chunk. This allows us to look at an individual chunk. We have heap chunks. This will display many a chunks. We have heap bins. This is of particular interest to me. I'm not going to get into arenas and set arenas today because this doesn't apply to this module. Yeah, that'll be a problem for a week or two from now. So if I do heap bins, what we see is there are many bins inside the heap. We have fast bins, we have unsorted bins, we have small bins, we have large bins, but what bins do we care about in this module? Just the T-cache. And what we see here up at the top, T-cache bins, index 1, size, hex 30, count 1, and then it has this chunk. What is size hex 30? Why is that hex 30? This right here. When I entered my size up above, I entered a decimal 28. If I print as hex 28, I asked for 1C bytes. Why is the T-cache entry at size hex 30? Anyone? Yes?
It first rounds the next hex 10, and then it adds the metadata, so that everything fits together.
Okay, so the response was, and I'm paraphrasing, that it's going to round up to the nearest hex 10, right, or 16 bytes, and then it is going to add some for the metadata. And that's roughly right? It's not a rule of thumb there. The thing to keep in mind is that the T-cache is set bin size, right? And when we say bin, what do we mean? This was something that came up on the Discord. And the comment was, well, it has to do with sizes, right? So if I were to malloc, which would be 1, I say I want a size of 64, and I want this in slot 2. And then I free slot 2. And we look again at the bins. We see now that there are 2 entries. Now I asked for 64 bytes. I asked for hex 40. What I got was a chunk of size hex 50. There is a difference between chunk and allocation, right? The allocation size is what userland is requesting. I'm saying I want something that is up to 64 bytes. But on the heap, the actual chunk that represents this is going to be larger than what I request because it needs to have that metadata. So now I have these 2 sizes. These are bins. The general term of binning, you can just think of it as sorting things into piles or buckets, right? It doesn't necessarily mean size, right? But for this module, we can think about it as just size, because it would be correct to say something is in the fast bins, and then within fast bins, there is a size sort, which we see here. And there's also the unsorted bin, which is a bin. We can just think of a bin as a collection of entries. But since for this module we are focused on the T-cache, the only bins that we're going to be interacting with are bins of certain sizes. Now, based upon this, what would happen if I malloced something of size 64 again? What do you think it would give me?
That same chunk you got before.
Okay, the comment was it would give me the same chunk that it gave me before. So when I malloced 64, it gave me this, right? And if I were to free it, when I freed it, it went here into the T-cache. We said the T-cache is an optimization layer that allows us to get these things faster. So when I malloc again, it is going to give me that same pointer, the same pointer I had before. I need to do a quick, I don't care. Oh, I'm not where I think I am. That's what I get for naming everything do.c. Oh, I didn't do this with, did I? Yeah. One sec. want debug symbols here. Okay. So we run it. I had malloc size 28 into bin 0. We had malloc 28 into 1. We had free 1. We had malloc size 64 into slot 2. We had free slot 2. We're in that same state. If I can type, we now see this is that pointers. This is slot 2. And if we examine the address that is there, why are you? No. What did I do? It is setting that. If I continue, if we malloc size 64 into slot 3, 164, 3. Cool. Then we should be able to print pointers. And we have this. Why are you? No, you shouldn't be null. This is what I get for not verifying pointers, char star. Let's make you 8 times 16. Need to do that down here. I'm a believer now. All right, let's say 1, 28, 0, 2, 0. Now you are mad. Gosh dang it. That's what I get. What we will do is not worry about these slots, and I will modify this here such that it will simply print out the pointer that is returned by malloc. Print F %P. Okay. So we malloc something to size 28 into 0, and it says, hey, malloc returned this right here. Why is that garbage? And we free slot 0. This has gone off the rails, guys. Malloc 28, 0, free 0. Okay, I have the pointer. Then if we go and we say heap bins, okay, things make sense now. There is our trunk pointer at 405 AC0, and we saw when I did the original malloc, what did it return? 405 AC0. Now, a thing to keep in mind when you're looking at this info in GDB, what pointer is returned by malloc? Is it the pointer to the allocation or the pointer to the chunk? The allocation is the usable data. So if I call malloc, I get the pointer to the data that I can use, right? And so right here, what we see is the pointer to the allocation. But when we think about layout of memory on the heap, we think in terms of chunks. And it's important to keep that distinction. Different tools will display different addresses for these chunks. Is it the chunk address or the allocation address? To demonstrate that, I will malloc and free another thing of size 28. So we will malloc 28 into slot 1. We will free slot 1. And then we look again at heap bins. I should have, oh wait, why didn't that work? I fetched the chunk from the T cache and then put it right back. So what I really need to do is malloc 28 0, malloc 28 1, then I need to free 1, it doesn't matter, free 1, free 0. Okay, heap bins. I now have 2 chunks in the T cache. Based upon the lectures, there is metadata, we said, and this metadata is in the chunk. Where is this metadata in relation to this address? Okay, somebody whispered before. So I could do heap chunks. Okay, this is going to show me some stuff. This is what's going on in the heap. And if we map what we see down below to what we see above, this is contiguous memory, right? So this is memory that is in order linearly. The listing here is that linked list that is the T cache. So we see 405 AC0, that is this one right here, and 405 AF0. These are right next to each other in memory. Why? Because I malloc something and then I immediately malloc something else. So the heap is just going to return the next available chunk of memory. Now we said that there's metadata. And if we focus on these 2 chunks right here, we see prev in use. What does prev in use mean? This is metadata. So the heap tracks whether or not the current chunk is in use, but if the chunk behind it is in use. And so when we look at 5AF0, it says prev in use. This is saying that this chunk here that begins at 405 AC0 is in use. But that doesn't make a whole lot of sense because we just said that we freed it. It's in the T cache. So why does the metadata say this is in use? Well, the T cache is an optimization layer, I said. This prev in use flag is used in big boy heap, right? This is used for consolidation and all sorts of other kind of mechanisms that are used after T cache. T cache is an optimization layer that was implemented on top of the heap. And so anything that's in T cache is going to lie because the T cache is a caching layer. And as a fast caching layer, it actually does not update this in use status. And so everything will be shown as in use in the T cache. Now if I grab this chunk right here and we examine, say we said 4 giant hex, and we'll go behind it. What do I see? Let's go a little bit more. Let's go like 8. Could we make sense of these bytes? I'm at 405 AE0, and that is going to be directly behind this chunk. Do these bytes correspond to anything? There's a 40, 50, 10, and 40, 50, 10 is pointing to this right here. Okay. That's something. How about this 31? That is the size, right? But why is it 31? Because we said up here when we were looking at the heap bins, it's hex 30.
Because of the 3 bits.
So the comment was because of the 3 bits. The flags data is stored in the least significant bits of the size. The most common one that you're going to see is the 1, which is indicating this pre-vin use. Because when we return an allocation, it's always going to be aligned by 8 bytes. So the least significant bits don't matter from an actual size representation. This would be AF0, pink, pink. Let's look at this one. I don't remember the order that I freed things.
Yeah, it's
This is probably what I want. Let's examine 8 giant hex of this one. Okay, so if we compare these, this was AC0. Why does this have 405 AF0 and this one has null? What is this? The next pointer. So when something is freed, the first value that's written, and it will be at the address of the allocation, is the next pointer. Now we said 5AC0 has something written. AF0 has null. If we scroll back up here, the order that I freed matters, right? Because this is a linked list. So when something is freed, it is pushed to the head of the list. The order that I freed here was slot 1, then slot 0. Slot 1 is AF0. Slot 0 was AC0. So what is at the head of the linked list? It's going to be the most recently freed chunk, which is this AC0. When that gets pushed onto the head of the list, we write the next pointer. And the next pointer is going to point to whatever was already there, the old head of that list. And that is what we are seeing with this representation right here with heap bins. We have AC0, then we have AF0. At AC0, it points to AF0. Counterintuitively, the arrows, in my opinion, point the wrong way. In Jeff, you read it from left to right. Any questions about that? No? Beautiful. Cool. So I don't know if Jan's lectures represent it this way, but we have a consistent theme here. As we have talked about file struct exploits, as we've talked about printf, we think about them in terms of arbitrary read, arbitrary write, arbitrary execution. I don't think I can show you arbitrary execution from the heap, but we can definitely do arbitrary read and arbitrary write. That is what a lot of this module's challenges are. Very similar to printf, very similar to file struct. This is a consistent theme here. We look at some weird machine or some implementation. We say, how can we make this arbitrary read? How can we make this arbitrary write? At that point, we have reduced this down to what are interesting things to read or to write. So, we'll run this bad boy. Now, this program is vulnerable, right? It's a poorly written program. What is the obvious vulnerability here? Like,
no index check for case 3, 4, 5.
okay, apparently I didn't do an index check somewhere. That isn't what I was going for, but that's good. There's a number of challenges where we don't do index checks and you could do some crazy side thing, but that's not relevant to what we're going for. I threw this together in like 3 minutes, right? Like an hour and a half ago. I'll give you a hint. It is in case 2. So it is in this right here.
You can free twice.
Okay, so one of the comments, you're not wrong. Okay, the comment was, I can free twice. And the answer is maybe, right? It is possible in this code to free twice, to free the same thing twice. It is not immediately possible to do that, right? But why can I do this? The answer is use after free, okay? Use after free, what this means is we free this value that is in this array. We free this pointer. However, did I zero out the value in the array? The answer is no. And so what that means is I can use that pointer again for future actions, right? And this has implications.
So the old pointer is still in the slot.
Right. Because where is this pointers array? Where is this? It is in memory? All right, that's a solid answer. Right? It is not on the stack. So if I included it in a function, then it would be a local variable to that function. So it would be in the function frame and it would be on the stack. In this case, I just declared it as a global because I'm lazy. And that means it is also read-write. So it would be in the BSS. But the point being is that we're reusing this same region of memory and we're not zeroing out that pointer. That is like the primary mistake that enables a lot of these things to occur. For example, if we were to print val in GDB, just so I have the address of it. All right, if I malloc size, I don't care, 28 into slot 0, I malloc 28 into slot 1, I free slot 0, I free slot 1. We've seen this. This is the state that I'm in, right? Where I have two chunks, they point to each other, and we said that the next pointer of this chunk points to the second one. But I can read and write to these chunks because the pointers weren't zeroed. So if I were to write to this address right here, which would be 1, what would I be writing? What is that? That's the next pointer. So since it wasn't zeroed, I could use my amazing program here and say read into 1. And, oh, it's not read. I should have just used words. 128.0, 128.1, 228.0, 228.1, 228, 3, 1, and 2, 3, 4, 5, 6, 7, 8. I didn't free?
Yeah, because the second parameter for free is the index rather than the size.
God dang it. Okay. How do I want to do this? This is why you write Python. 1, 28, 0, 2, 28, 1. Dang it. 1, 28, 0, 1, 28, 1, 2, 0, 2, 1. Okay, now we read into 1. Well, why does it have to be 1?
Is that currently at the tail end of the Gcache?
It's at the head, right? So we want to make sure that what we're writing to already has a next pointer. All right, 1, 2, 3, 4.
I think for read you have the arguments flipped. I think
No,
it's
we're
size.
segfaulting right here. It turns out I just can't write code. P slot. Oh, that would be why. Slot. What is slot equal? Scan FD into the address of slot. What is slot? Slot is an int. That looks right. What am I doing for read? That looks right to me.
I think when you called read, you.
Oh, I have to give it 2 arguments. Gosh. 128, 0. 128, 1, 2, 0. 2, 1. We'll read. What do I want? Size first. I'm going to read 8 bytes into slot 1. I'm a believer.
All right, let's do it.
1, 2, 3, 4, 5, 6, 7, 8. Okay. Now we can control C. Give up on Python. We're rebels. And if we go to heap bins, what we see now is Jeff doesn't know how to make sense of this, right? We had that chunk, and then when it tries to find the next chunk, it says it's a corrupted chunk. And if we were to examine the giant hex, where we wrote, we see these A's. So that is the next pointer. Now I can, in theory, make this return whatever I want. So what if I did, I got to go reference my own code. Case 3, I want to read 8 bytes into slot 1. Oh, I would need Python for this because I have to write the bytes. We're doomed. All right, let's speed run it. User bin env python 3 from pwn import star context arch amd 64 p equals process a dot out p dot send. What do I want? Show me the pretty menu. 128 0, and I want send line. Then we're going to free. Then we're going to free. Then we're going to read into 8 bytes into slot 1. Then I'm going to send P64 of that address. Didn't crash.
Because you're doing malloc. If you do malloc, it will crash.
Well, you told me this would crash. This didn't crash. Okay. So if I have this, and let's GDB it. Heap bins. Oh, we are before that. Bam. Heap bins. Come on, Jeff. Heap bins. Jeff has abandoned me. Unsorted small. Why am I not seeing this?
Because we're inside Python.
Is that really? All right. I will figure out whatever the heck is going on with that, and we will.
Should you do like receive first before you send?
Possibly. I don't think that's the issue here, though. Comment was, shouldn't I receive? And that is possible, right? If the buffer got full. Yeah. So it was from Python here. But now what we see is I have written it so that it thinks there's two chunks, and the second chunk is that pointer to that not so secret value. So this is where things get interesting. If I malloc 1, okay, then I malloc a second one, we segfault. Why are we segfaulting? This is what I was being advised would blow up. Right?
Yeah, I don't know if this version implemented that feature, but you better to set alignment, just the 0 the last byte.
So this libc doesn't have the Tcache stuff, the earlier ones, or not Tcache.
Alignment check, like Tcache again.
Yeah. The alignment check is with safe linking. It's next version of libc. Why did we blow up? R8. Oh. So what is that checking? It's looking at the address I gave plus 8. So we said at the address, it is the next pointer. What's after the next pointer?
Tcache key.
Right, the Tcache key, or in this version of libc, it would be the Tcache per thread struct pointer. Does anyone know what the Tcache per thread struct is? It's in the lecture videos. I think Jan calls it Bjorn or something. He gives it some crazy name.
Then go with like some umlaut somewhere.
Right. If we examine 4 giant hex at the location that I gave it, right? This is all a string, and so it's trying to zero out the Tcache per thread struct, but it can't because it's in read-only memory, I'll bet.
Oh, wait.
Yeah? You agree?
Yeah.
It is not alignment. It is Robert's lame code. Okay. So, let's fix that. We'll grab this, and we will put it inside of main, so it is now on the stack, which should be writable.
Wait, it's the pointer, so I mean, you better to use strgut.
Oh no, not this again, man. Right. I'm not doing this again. All right. You know what I'm gonna do? I'm not. Okay, we're gonna do this. I'm a believer here. We all collectively fail to write C code. Yeah, all right. Twitch, you're just a little bit behind the curve there. Now it doesn't like val. Where am I using val? You know what? Case 5 doesn't matter. Okay. We have this. We have our amazing Python code. We're going to automate that right there. We'll run our do.py. Oh, you are correct, sir. That's going to be a heap address now. So now I need this. We'll have to do that live. PSAUX, grep a.out.
I think that's a stack address.
Yep, and that's where we're going to have to grab it from GDB. 6594. Okay. BT backtrace frame 2. Print val. Print the address of val. Now I have that. You agree?
Yes.
Problem. I can't input those bytes, can I?
So you use strdup.
I don't want to hear about strdup. I don't want to hear about it.
Because of ASR, so you cannot use it. Or you have to use the stack address.
This guy, man.
I love that.
I'm just gonna like do random things to spite you. That's how this is gonna go. I'm gonna run out of time. This class. I wish it was longer. Okay. I have this. Did I get it? Oh. Okay. Yes. AUX. Sudo GDB A 685. We can gab. GDB A. VM map, that works. VM map this address. It is now read write. Okay. And now I have that address. So, P, send line. Actually, I just want to send. Send P64 of that address. Then we will malloc twice. All right, do you believe? Or are you a doubter?
I believe it will progress.
Okay. All right, we didn't blow up. And now, if I write from 1, I have to look at my own code to verify that that is how this program works. Where is size? All right, we will write, I don't care, 20 bytes from 1. No! So close. But what you can do that we failed was we will get it to return that pointer and print out that value. Now, if I have a pointer here and I have the ability to read and I have the ability to write, then I can get an arbitrary read or an arbitrary write to anywhere that I want in memory. From that point, it's how do I use this? All right. I expect people to get stuck on 16. 16 and safe linking will be the focus of office hours on Friday. All right. Because I know that will be a point of contention. I failed to properly demo, but conceptually, do you get where we're going with it? Yeah? Okay. With that, I will end the stream. I appreciate everyone hanging out.